Hi everyone. So I'm Vaishali Karle. Currently, I'm working as a senior scientist in Alvotech as an upstream process development team. So today I'm going to share the design space optimization, especially the process optimization of biosimilars using a JMP DOE case study model. So we will start with the introduction. The introduction includes the process overview and the problem statement. So in the process overview, it says that we are designing the design space or deriving the design space using the quality by approach or QBD approach, we say. So for that, we have explored the DOE in the JUMP software. So the goal was to derive the design space for the better understanding and the better control of the process. To achieve this goal, we wanted to have, or we wanted to improve the efficiency with a streamlined or easier DOE designs with a fewer runs, like less than 30 runs, and to identify the parameters which will help us to reduce the cost and reduce the time with the greater efficiency. So to achieve this goal and to solve the problem, we started with the strategy, or we say it as a QBD based process flow approach. In that, if we see, we have the selection of the operating parameters, or we say as a critical process parameters based on the FMEA, or we say it as a risk assessment approach. So based on that, we decided the operating parameters, and then categorization of those parameters into multivariate and the univariate study so that we can use them for the DOE model. So we have used the like a DOE model selection approach. If we see in the table, we are having total 5 parameters or factors, that is initial temperature, final temperature, pH, DO, and VCD. These are all our process parameters, and we were having the ranges of those parameters as a +1, -1, and 0 as the center points. So we took this all 5 parameters in the DOE model, and we started with 3 designs, that is definitive screening, custom design, and classical designs, that's central composite design. After running all these factors into the DOE model, we have seen a few models with the run numbers, then central points, and how many total runs it will give. And we were able to select the design based on the power analysis or the design evaluation that I have included in the next slide. So the DOE model selection approach, design 1, we were having definitive screening. So with the definitive screening, we were getting 14 number of runs with 2 center points and actual total 16 number of runs. But when we started the power analysis and the color map correlation, basically the design evaluation were not very much satisfying for us. It was giving a lot of confounding effect. Even though the run numbers are less, the confounding was more. So we went ahead with the second design, that is custom design. With the custom design, we were getting 22 number of runs with the 2 center points and 24 runs. But again, if we see, the color map correlation was showing a lot of confounding effect, and which is not very trustworthy approach to get us the predicted values for the outputs. So we went ahead and deselected first 2 designs, and we went ahead with central composite design, where it shows that the central composite design was giving us total 26 runs with the 2 center points and 28 final number of runs or experiments, we can say, which we thought of having a more like approach of more analysis of the design. So after like complete power analysis and the color map correlation, we can see there is very less confounding, or whatever the interactions are there, they are with the like main effect is more prominent there, and the confounding is only for the quadratic terms, which is acceptable, and we can go ahead with design that was more satisfying for us while designing or while selecting the DOE approach. So we decided to have central composite design, and we went ahead with total 28 number of runs and execution of the experiments to get the final data. So after execution of the experiments, we went ahead with the statistical evaluation of the experimental results. So we have put all DOE analysis into the fit model approach, or all DOE data into the fit model approach, and then with the fit model approach, we decided to go ahead with stepwise regression with the forward AIC stopping rule. And for that, we got parameter estimate, summary of the fit, analysis of variance, all the outputs of the fit model approach, which is helpful for us to get the most significant factors. So when we did the complete fit model and fit model approach analysis, we received the pH, DO, and temperature, few of the factors as very significant factors. And we went ahead with the predicted formula or predicted values for those factors. So after finalizing the fit model approach, we went ahead with the factor profiling. That is the most significant or helpful visualization of data for us, which is most like crucial for deriving the design space, because it will give us more like a picturized form of our data. So in the factor profiling, we went ahead with the interaction profile, then prediction profile, and the contour profilers. So prediction profiler, we treated pH as categorical factor to account the deadband settings around the pH set point. So if we can see in the figure 1, where we have included the prediction profilers, where we can see the pH as levels like L1, L2, and L3. That was the little modification apart from the factors, apart from the settings we have selected during the DOE. So in figure 1 of the prediction profilers, I can explain that the factors are pH, DO, initial temperature, final temperature, CDVCD, are compared or analyzed against the predictor formula for the one of the quality parameters, that is HHL. So we wanted to see the effect of the factors with the quality outputs. So if we see the pH, DO, initial temperature, final temperature, and CDVCD are quite stable, so which are not having much effect on the HHL, but the DO percentage are is showing the most significant factor, and which is crucially impacting our output factor or output parameter, and pH as well. So we compared the predicted values against our historical data, that is 3SD ranges, and we limited our expected or desired output value to the plus 3SD range. Like our output factor, that is HHL, should not go beyond the 3SD range. That is what the desirability or expected values we wanted to or limit to. So to derive the design space, we like use the historical ranges also and the predicted values also, and the design space was derived as shown in the figure, that is green, what we can say, green colored area, which is derived or which is said as predicted as a design space area, or acceptable ranges area, we say more precisely in the process. So that means the design space was showing that if we have the DO, or if we have factor it in this range, that means we will get our quality parameter or output parameter within our specified limit of plus 3SD. So this is the way the predicted values or predicted formula was extremely helpful, or like extremely helpful to get to the accepted ranges or design space ranges. In the next slide, I have included the interaction profiles as well. So interaction profiles were helpful to see the effect of one factor changes across the another factor. So if we are changing one factor, how it is affecting, or is it having any interaction effects with the other factor. That was helpful. So in this interaction profiles also, we have included the green color area to show as a design space areas for the factors studied, and the contour profilers, we were able to see if we have any factors going outside of our ranges decided. And if we see like basically in the contour profiles, we were not utilizing the visualization part more, we were utilizing the like minimum maximum ranges, and where our data falls, if we make the changes in the factor, that is the more satisfying or helpful usage of the contour profilers. But basically prediction, interaction, and contour profilers, all three of them were extremely useful to derive the design space ranges or acceptable ranges for the factors studied. So all in all, so design space or acceptable ranges were derived using DOE model. And if we see, the design space is extremely helpful for supporting the process robustness by defining the optimal factor settings and ensure that we were getting the consistent product quality and to reduce the variability. So um, this entire study was basically more towards the robust and consistent process like achievement. So this presentation is relevant for the process development professionals. It is like offering very great insights for DOE strategies to define design space for process team and optimize parameters. And if we want to achieve high efficiency with reduced cost, time, and rework. So these all experiments were carried out with JMP 16 data analysis, DOE model, everything was used in JMP 16 software. And now currently we are starting using JMP 19 and JMP 19 Pro as well. But the experiment were that time used or carried out with JMP 16. And we have some JMP documentation used or like referred for this. Currently, I'm not including any like JMP files here, but we have some JMP